Thank you. Thank you, Luca, for your invitation and for your introduction. The title of my talk today is Challenge in Very High Cycle Fatigue and Numerous Cycle Preparation Model. And here is the outline of my talk today. After the introduction, I will be talking about basic characteristics of very high cycle fatigue. Next is major challenges in very high cycle fatigue. And then numerous cycle preparation model, followed by further results regarding NCP model, and finally concluding remarks. In the beginning, I would like to mention briefly what is very high cycle fatigue. Very high cycle fatigue is fatigue damage and failure beyond 10 to 7 cycles of loading, and the applied stress is quite low below conventional fatigue limits. And here are two early examples showing the very high cycle fatigue cases for high strength steel and titanium alloy. And we can see this part beyond 10 to 7 cycles of loading, and also here beyond 10 to 7 cycles of loading, very high cycle fatigue regime. So I would like to say, due to the contributions by some early researchers, they initiated the research of very high cycle fatigue in the 1980s. And here I would like to mention about the regions of very high cycle fatigue research. I would like to say very high cycle fatigue is a cutting edge regime in fatigue research, and also is a new regime because very high cycle fatigue research is only 40 years old or less than 40 years old, and the total fatigue research history is about 170 years. And very high cycle fatigue is an important area of research because very high cycle fatigue behavior mechanisms are different from the cases of high cycle and low cycle fatigue. And also some advanced materials and structures required very high cycle fatigue knowledge, and also engineering structures and components, they all require a large number, like 10 to 8 cycles of safe performance. Like review paper said, very high cycle fatigue is a first difficulty and imponderable issue for safe life of railway access. So today I would like to share with you the challenges in very high cycle fatigue and the numerous cycle preparation model we proposed. So after such major content of the talk, I would like to share you this type of topic. And in these contents, I will use high strength steels and titanium alloys as examples. So now the second part, basic characteristics of very high cycle fatigue. 4 points in this part. First, internal crack initiation. Second, SN curve. Third, crack initiation life. And fourth, crack extension rate in initiation. And the first point, internal crack initiation. We all know that the fatigue crack initiation in low cycle and high cycle fatigue is due to persistence depend. But in very high cycle fatigue, the crack initiation and growth mechanism is different. Normally, the crack is always initiated in the interior of the specimen, like this morphology, and also showing a kind of fisheye feature containing a rough area called FGLS, fine granular area. So for high strength steel, this schematic showing this process, crack initiation from an inclusion and a rough area, and next fissile region, and then find a fracture. And then we try to measure the size of FGA, this crack initiation region, and the value is between 40 and 100 microns, like the data showing here. And also, we try to calculate the data value for this region is in relation with the price tricks and the size of the defects. And the value for the delta K FGA is between 4 and 6 megapascal root meter, like the data showing here. And also, we collect a large number of data from the literature, and then we put two boundaries. One is the upper bound of 6 megapascal root meter, and a lower bound of 4 megapascal root meter. And we can see almost all the data points within these boundary, these two bounds. So we said that, or we proposed the size of FGA, this the initiation region during very high cycle fatigue, is an intrinsic characteristic size for internal crack initiation. And then we can use this size for the fatigue life estimation and for the crack extension rate in the initiation stage. That's what I said for the crack initiation, the prediction and extension, crack extension rate estimation. And then I would like to talk about the case of titanium alloy. The crack initiation is also a fissile feature, but for titanium alloy, the initiation support is not an inclusion, but is some facets in the initiation area due to the cleavage process of the titanium alloy, always alpha phase. And this is the schematic showing this process. The formation of facets act as the crack origin, and then the area called RA as crack initiation region, and then the fissile region, and then final fracture. Again, we also measure the RA size, and it's between about 120 and 390 microns. Is also quite stable in comparison with the fissile size. Is a large range for fissile size, and also the delta Ki value is stable for titanium alloys. So we try to analyze the threshold value for the crack initiation region. We use the formula for plastic size at the crack tip as this, and also we use a formula to correlate microstructure characteristic size in relation to materials parameters of shear modulus and yield stress. And we assumed when the platform size of the crack equals to the characteristic size of material, the FGA formation is completed. Thus, we can obtain this result to show the delta K FGA. This value is just in relation to shear modulus and burst vector of the material. So it's very interesting and important, showing that delta K FGA or delta K TH is a function of burst vector and shear modulus of material. For steel, this value can be calculated as about 5.5 megapascal root meter, and this is in agreement with experiment. That's the first point, and then I will mention the second point, SN curve. These are the data from a kind of round-robin test organized by Professor Sakai. The left part is the crack initiation from surface cracks or surface crack initiation cause the fatigue failure, and the right part is from the internal crack initiation. And we can see it's a kind of it's a kind of called the duplex SN curve or stepwise SN curve. And for high this high strength steel, but for titanium alloy is also a kind of stepwise SN curve trend, and is also due to surface crack initiation and subsurface or internal crack initiation. So due to the different type of crack initiation from surface or from interior, they will result in different trends of SN curve. That's the second point. And then third point is about crack initiation life. We have mentioned previously the delta K value and is a threshold for crack initiation. And also we assume Paris relation can be used to describe the crack growth after the initiation, that is after delta K FGA. And then we can use Paris relation to calculate the fatigue life from the boundary of FGA to the fisheye, and then from the fisheye to the critical size. Like here, from boundary of FGA to boundary of fisheye, that's N sub 1, and then from boundary of fisheye to final fracture point, that's sub 2. And for example, N sub 1 can be written like this type, and we also can use such parameters for calculation. After this, we can obtain the initiation life by the total fatigue life minus N sub 1 and N sub 2. Therefore, we are able to obtain the result for high strength steel. This result shows that at very high cycle fatigue regime, the initiation life is larger than 95% of total fatigue life here. And if the fatigue life is 50 million cycles, and the initiation life is larger than is here larger than 99% of total fatigue life. And for titanium alloy, the value initiation life for very high cycle fatigue is between 96 and 99%. So we can say that for the fatigue damage, including very high cycle fatigue, the fatigue life almost consumed by crack initiation process. That is the formation of the initiation area of initiation zone of FGA or I. And then the fourth point about crack extension rate in initiation. We have been talking about the initiation life, and also we know the size of this initiation zone, and then we can obtain an average value for crack initiation extension rate. I like to use the term extension instead of growth. Okay, extension rate with FGNI for high strength steel and for titanium alloy. And the value for high strength steel is 10 to minus 12 and 10 to minus 13 meter per cycle. And for titanium alloy is 10 to minus 11 and 10 to minus 13 meter per cycle. It's very slow. And I would like to mention some indirect measurements of these extension rates. This, I think, is the first case by Stenchek and her co-author to show that FGA, the extension rate in FGA is 10 to minus 12 meter per cycle. They use this type of specimen to perform this measurement, and then they compare the fracture surface morphology with the tubular specimen and the round specimen, and then to get this value. Another indirect measurements is use a kind of repeated two-step testing, and they are able to catch the pitch mark on the fracture surface, but their measurement is the area of fisheye region beyond FGA, the initiation area. So they obtain the data in this region, and then they try to infer, or they try to estimate the crack extension rate in the initiation region, and to give the result of 10 to minus 13 and between 10 to minus and 10 to minus 14 meter per cycle. And also another example of indirect measurement use variable amplitude testing for it's a structure steer, and this result is a high carbon bearing steer, and the result is 10 to 11 and 10 to 12 meter per cycle for the fisheye. So such attempts or such efforts are devoted to the crack extension rate in the fisheye region outside FGA. So we are expecting direct measurements of crack extension in the rear initiation region of FGA or RA. And this is the first case of crack extension rates obtained in high strength steel, and we use a kind of repeated two-step cycling to catch the crack growth traces in the FGA stage or FGA region, and then we are able to obtain the crack extension rate in this region directly. And the result showing here to show the rate is between 10 to minus 11 and 10 to minus 30 meter per cycle. And we are happy to see that the result here can be well connected with the growth data in the FGA, in the fisheye region outside FGA, meaning that the initiation extension rates and the early growth stage crack rates. So from the beginning and then to the early growth, they can well connected. This we are happy to see is data trend. This is a step cycling for a stainless steel, and the results shows that the data is between 10 to minus 12 and 10 to minus 11 and 10 minus 11 and 10 minus 12 meter per cycle. I think the internet is okay now, right, Luca? Can you hear me?
To be honest with you, it's a little bit, how can I say, sometimes it doesn't work, but I think that we can follow, so please keep going. In case I would stop.
I mean, the internet is okay, right?
A kind of. Okay, your connection is a little bit slow, but I think that we can follow what you are saying. Or maybe you can, Youshi, since we are focused on your slides, maybe you want to turn off your camera, so probably it might help. Stop a video. You have a button down in the screen on the left hand side.
You mean turn off the?
If you can stop your video and you can keep it talking, and we would follow your presentation by keeping watching the slides. But it seems that, okay, please keep going. It seems that now it's working, so please keep going. In case I would stop you. Thank you for double checking. Thank you. Okay,
so and then now there's another direct measurements of crack extension rates by very new kind of method this synchrotron radiation microcomputed topography, and they can use this method to observe the crack growth message, and then to obtain the crack growth rates between 10 to minus 11 and 10 to minus 12 meter per cycle. So we noted that the extension rate initiation is 1 to 3 orders of magnitude smaller than Burgers vector, and this can be simply expanded that the crack extension is a kind of inhomogeneous and discontinuous in 3D crack age. Okay, now the summary of this part, I would like to show this picture of crack initiation and early growth for high strength steel and titanium alloy. And we said that the initiation region of FGNI is a characteristic region for crack initiation, and the value of delta K of the delta KFG or delta KI is almost constant and is a function of Burgers vector and shear modulus. And more than 95% of total fatigue die is consumed in the initiation region. And also the crack extension rate is very low, between 10 to 11 and minus 11 and 10 to minus 30 meter per cycle. So in this stage, we say very high cycle fatigue is a cutting edge research regime. And also very high cycle fatigue contains unique characteristics and mechanisms. So we would ask, what are the challenges in very high cycle fatigue? So the next part is major challenges in very high cycle fatigue. I would like to mention 3 points in this part. The first is loading frequency effect. Second is cracking evolution detection in initiation phase. And the third one is parameters and models to characterize crack initiation and predict fatigue life. About loading frequency effect, I will show you this case, this example. For the high strength state of the material, the frequency effect is limited. But for the low strength state of the material, the frequency effect is very large, and the result, the fatigue strength by ultrasonic frequency, that's very high frequency, is larger than the conventional frequency. And this is explained by these descriptions. Because for the high strength states, the microstructure is quite is a kind of refined microstructure and contain large barriers, large amount of barriers, and they can restrict the dislocation movement. But for the low strength state material, the barrier is less, and there's limited restriction for the dislocation movement. So the dislocation moving distance will be inversely proportional to the loading frequency. So for this case of low strength state material, the damage per cycle will be larger than the damage per cycle of ultrasonic loading process. So we say that for low strength material, frequency effect is remarkable, but high strength material frequency effect will be diminishing. And I also would like to mention the temperature rise under different loading frequencies. That's a loading frequency effect. We have this type of result to show the specimen without cooling under ultrasonic frequency loading, the temperature rise is about 70 or between 70 and 130 degrees. But if the specimen is subjected air cooling, the temperature rise is somehow smaller. For the case of very high cycle fatigue testing, the temperature rise is less than 25 degrees. But for the loading frequency is 120 hertz, is a kind also not a kind of conventional frequency. The temperature rise is very limited, less than 3 degrees. So we will say high frequency, especially ultrasonic frequency, will cause specimen temperature rise. And if this happens, it will reduce the material strength and also change the frequency response, and will reduce the fatigue strength. So for the frequency effect, there's about three orders of strength rate difference between conventional fatigue and ultrasonic fatigue. So I mentioned before, those strength state, the frequency effect is remarkable, but high strength state frequency effect is limited. But and also high frequency will cause specimen temperature rise. And also I will mention this, for BCC and HCB materials, the frequency effect will be sensitive, and for FCC material, the frequency effect will be less sensitive. But this topic, I think, is also a challenge for the very high cycle fatigue research. It needs in-depth investigations. The second challenge is crack evolution detection in initiation phase, and this is a promising method, that is synchrotron radiation microcomputed tomography. This is from the Nakamuna's group. They use this new method to observe the defect of crack initiation and early growth, and also they measure the crack growth or extension rates between 10 to 11 and 10 to 13 meters per cycle. And another example is by Professor Parinda's group, and they use a kind of in situ synchrotron ultrasonic testing. The difference between this one and previous one is they use ultrasonic testing to accelerate the fatigue process, but the previous one they use a frequency of 400 hertz. So it's a kind of difference testing. Use the similar method to detect the small damage evolution process, but it's, I think, also is in the beginning stage. And in this case, they're very good or very clever to use a kind of artificial defect inside the specimen, and to detect or to observe the defect evolution or defect development during the loading process. And if we can explicitly reveal the crack initiation and early growth, this will lead to a significant breakthrough of very high cycle fatigue research. And the third challenge is parameters and models to categorize crack initiation and predict fatigue life. Here, I would like to mention the model by Murakami, and this is a very often used, and also the concept and parameter of root area is often used in the very high cycle fatigue assessment, and this model correlates fatigue strength in relation to the material group parameter and also the defect size. And in recent years, we also propose a model to correlate fatigue life to the loading stress and yield stress and FGA size and inclusion size. And also, I would like to mention the concept of fatigue indicator parameters. This is to be used in very high cycle fatigue, and previously is quite often used in low cycle and high cycle fatigue regime. And this topic was in the first Global Life webinar by Professor McDowell. I think we can refer this aspect to his talk, in his presentation, and is available on the website. So I would like to say the third challenge of parameters and models is a very important aspect, because the parameters should be measurable and computable, and models should be simple and applicable to, and also they should reflect the physical process and mechanism of high cycle fatigue. So the quantitative describing the damage behavior and correctly predicting the fatigue property of very high cycle fatigue is a very important challenge in this area. So here I mentioned the three challenges in the very high cycle fatigue. And in this stage, I think we may ask two questions. The first is, what is the nature of the initiation region? And the second is, what is the mechanism of FGA and I formation? So this is the fourth part of the talk, numerous cycle tracing model. First, I would like to mention some previous models. The first one is hydrogen-assisted FGA formation, meaning that the existence of hydrogen will cause the rough fracture surface at crack initiation. And the second one is called dispersive decohesion of spherical carbides, meaning that the existence of carbides will be the crack initiation point. That is the decohesion between the carbides and the matrix to form a rough surface at crack initiation. And the third one is called fine granular formation ahead of crack tip to form the fine granular area, meaning that at the crack tip, the plastic deformation will induce the microstructure refinement and then the crack initiation growth to form a rough fracture surface. And the fourth one is called local grain refinement at the crack tip to form FGA. This one is somehow similar to the third one. But these previous models can explain different experimental cases. For example, for the case of 10 to 7 cycles loading, the FGA and the rough surface, fracture surface are quite evident, but for the loading of 10 to 5, there's somehow smaller loading cycles. The FGA morphology is not very, is not such kind of rough surface of FGA. So for different loading cycles, the morphology can be different. And for different loading stress ratio, also may have different morphology. For -1 stress ratio, the rough surface of FGA is evident, but for 0.5 stress ratio, the FGA is cannot be observed. It's not FGA morphology. So at this stage, we try to find what is the nature of the initiation region of FGA and I. And we use the specimen of high-strength steel and to observe the fracture surface of rod morphology, and we use the spatial polishing method to observe the rod surface of about 650 nanometers thick. And then we cut a fifth sample to observe the fracture surface to reveal that the fracture surface is a nanograin layer between 500 and 800 nanometers, and the matrix maintained original tempered microstructure, and the average grain size is about 50 nanometers. And we also use a specimen to observe the both fracture surfaces and to reveal that both surfaces contain nanograin layer on the fracture surface. So we say that the nature of FGA in high-strength steel is a nanograin layer, and the thickness is between 500 and 800 nanometers, and the grain size is about 50 nanometers. And for the case of titanium alloy, we also observe that fracture surface of RA initiation region by a fifth sample to reveal that the thickness is between 800 and 1500 nanometers. And also the microstructure is refined, and this is equiaxis microstructure. And also for the microstructure of numerous feature, the fracture surface is also refined. So for titanium alloys, the I region is a nanograin layer, no matter how microstructure equiaxis or laminar ones. And then we propose a model of numerous cycle placing model. Crack initiation first at inclusion, and then the nanograin formation at crack wake by repeated placing between the crack surfaces. And this process is in relation to the crack closure and residual stress realization. And then this process continues to produce the nanograin layer, and also the within including the growth of the crack, and the new crack also can repeatedly compress to produce or to refine the microstructure. And at the transition point, this stage is terminated, and these formulas can be used for definition of the size of the FGA, and also the delta K value of FGA. So for this model, we may have two predictions. First is nanograin layer. We are inversely in relation with the stress ratio. For positive stress ratio, nanograin layer will be less possible. The second one is even for negative stress ratio, but the loading cycle is insufficient, the nanograin layer will be less possible. So we perform some further tests, and this one is -1 stress ratio. We can see the diffraction pattern is a kind of slightly elongated spots, meaning there's a couple of grains in the diffraction circle. And for the stress ratio 0.1 and 0.3, all the diffractions are isolated spots. So this is the verification of the first prediction. And This is the second verification. This is the verification of the second prediction. Also, we use titanium alloys. The loading is under 0.5 stress ratio, and to see no microstructure refinement happens in this case. So this is also a verification of first prediction. And also there's a numerical simulation by German researchers. Their result shows that under the minus or negative stress ratio, there's a large contact stress. But for positive stress ratio, the contact stress is almost zero. So the numerical simulation supports the NCP approach. Okay, now the 5 parts, the further results regarding NCP model. The first one is structure steel, because in the previous cases, they are all the steels with hard carbon contents, and this one is kind of middle carbon content. We see that in the 10 to 8 cycles of loading, the rough surface of initiation region is quite well developed, but for the next cycle of 10 to 7 is less developed. And also we observe this region is quite refined microstructure of nanograins. So we said FGA and nanograin layer is more pronounced in 10 to 8 cycles of loading, but is less pronounced and discontinuous also or discrete in this loading cycles of 10 to 7. And the second one is high strength steels at variable cycling. The previous one is not variable. So we also saw here is the variable cycling. Also a rough area is a nanograin layer. So it's a nanograin in surface layer of FGA region of variable loading. The previous one is constant amplitude loadings. And also the 3 further result is titanium alloy with equiaxis microstructure. The important thing is for this case, under negative and the -1 stress ratio, the initiation point is very close to specimen surface, and we examine these parts to reveal the microstructure with refined and also a kind of nanograin layer. So we said that the nanograin layer or refined microstructure can be formed in the air environment. So this is very interesting. And the fourth one is grain size distribution in initiation region of high strength steels and titanium alloys. We tried to measure a number of flip samples. This is the case of high strength steels, and we also observed the titanium alloys to reveal the grain size distribution. This for high strength steel, this for titanium alloy with duplex microstructure and with equiaxis microstructure. Is between for high strength steel is between 50 and 70 nanometers, and titanium alloys is about 100 nanometers, and for duplex microstructure and 50-60 nanometers for equiaxis microstructure. And also we are able to measure the thickness of the nanograin layer for high strength steels and titanium alloys. And we also define or we propose a quantity, a normalized quantity of D star. Here is L over L0. L0 is parameter of continuous diffraction ring. L is the total length of this continuous ring. By this parameter or by this quantity, we can describe the evolution of refined grains for high-strength steel and for titanium alloys. So we can say that for high-strength steels, the grain size is 50 nanometers for -1 stress ratio and about 73 for -0.5 stress ratio, and thickness is between 300 and 600 nanometers. And for titanium alloys, the EQX microstructure, the grain size is about 60 nanometers, and thickness is about 200 and 500 nanometers. Duplex microstructure, the grain size 110 nanometers, and thickness 700 and 1500 nanometers. And also, the nano grain size is increasing with the crack growth path away from the fracture surface, and also is associated with gradually reduced contacting actions between crack surfaces. We can see that this phenomenon. And then the 5 cases of further results of dual microstructure of titanium alloy. The dual microstructure is laminar mixed or laminar and equiabsent. We can see the internal crack initiation, and also the FGA or the RA region is the refined or nano-sized microstructure. So we say that for titanium alloy with laminar and equiabsent microstructure, the crack initiation region is nanogranular, but remain original microstructure at positive stress ratio. So now I would like to conclude my talk. The first, I would like to show you again the pictures of high-strength steel and titanium alloy, and I emphasize that these parts, the initiation is very important. The FGA region for high-strength steel and I for titanium alloy, because this part consume more than 95% of the divide, and also the extension rate is very small, very low. The second concluding remark is the challenges. I mentioned 3 challenges. The first one is frequency or strain rate effect. The second one is the evolution of initiation region of ACN and IA. The third challenge is the parameters and models to be developed. The third concluding remark is the NCP model. We mentioned this one. I would like to say there are 2 conditions for NCP model or NCP process. The first one is compression loading should be maintained. The second one is sufficient number of loading. And this process is in relation to crack closure. This is resulted from localized plastic deformation and residual stress granulation and positive phase transformation. And the formation of nanograins and refined microstructure, it can be continuous and also can be discontinuous or discrete. And the thickness can be large or small. It depends on the materials, depends on loading conditions. And also I like to say the NCP concept is possibly to create new approach to produce material parts with nanosize or refined microstructure. So this almost the end of my talk. We are all climbing the mountain of fatigue and fracture. We have some problems, we try to get solutions, and we may get some success. But I don't think we can finish. We always have new starts. So thank you very much.